Hello there, and welcome to Umber Dreams Archives. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, adjust your pillow, let your body sink into whatever surface is holding you. Where in the world are you watching from? A quiet bedroom where the day has finally released you? A cozy corner where you can finally let your mind wander? Tonight we're going to explore one of the most enduring mysteries in all of science. Why we still don't truly know how the dinosaurs died. We'll walk through the asteroid theory, examine the volcanic eruptions that shook the world, contemplate the climate shifts that may have sealed their fate, and discover why, after decades of research, the answer remains beautifully, fascinatingly uncertain. It's a journey that spans 66 million years and touches on everything from tiny crystals in rock to global catastrophe. But don't worry. This isn't going to be an alarming dive into apocalyptic scenarios or disturbing extinction events. Instead, we'll move slowly and carefully through the evidence, the theories, the discoveries that have shaped our understanding, taking our time with each revelation. By the end, I think you'll find there's something deeply peaceful in accepting that some mysteries remain open, that uncertainty itself can be a kind of answer. If you enjoy these calm explorations into the deep past, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these slow drifts through time. So settle in, let your shoulders drop away from your ears, take a slow breath and then another. And let's begin our slow drift through the end of the Cretaceous, through theories and evidence, through what we know and what we're still discovering. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story unfold across millions of years. Let's begin 66 million years ago, on a day that seemed like any other. The sun rose over a world that had belonged to dinosaurs for 165 million years. Tyrannosaurus rex hunted in the woodlands of what we now call North America. Triceratops moved in herds across flowering plains. Pterosaurs soared above oceans where mosasaurs prowled the depths. The world was warm, lush, thriving. And then something happened. Something that would end not just the reign of the dinosaurs, but 75% of all species on Earth. The question that has haunted paleontologists ever since is deceptively simple. What was it? What event? What combination of catastrophes, what shift in the planet's systems caused the most successful animals in Earth's history to vanish? For most of human history, we didn't even know dinosaurs had existed. Their bones were mysteries, dragon legends, giants' remains. It wasn't until the 1800s that we began to piece together the story of these ancient reptiles. And it wasn't until the 1980s that we started to understand how suddenly their story ended. The evidence was there in the rocks, in a thin layer of clay that circles the globe, marking the boundary between two geological periods, the Cretaceous and the Paleogene. Below that line, dinosaur fossils. Above it, nothing but emptiness. That boundary layer is just a few centimetres thick in most places, a few centimetres representing what might have been days or years, or perhaps a few thousand years of deposition. It's a memorial written in stone, a gravestone for an entire world. And within that clay, scientists discovered something unexpected. Iridium. Lots of it. Far more than should exist in Earth's crust. Iridium is rare on our planet's surface, but it's common in asteroids, in the debris of space that occasionally falls to Earth. This discovery, made by physicist Luis Alvarez and his son Walter in 1980, changed everything. It suggested that something from space had struck the planet with such force that it scattered extraterrestrial material across the entire globe. The impact theory was born, and for many people the mystery seemed solved. An asteroid killed the dinosaurs. Case closed. But science is rarely that simple. As we'll discover together over the next few hours, the more we've learned about the end of the Cretaceous, the more complex the picture has become. There were volcanic eruptions on a scale almost impossible to imagine. There were climate changes already underway. There were ecological pressures building. The asteroid may have been the final blow, but was it the only cause? Was it even the primary cause? Or was it simply the most dramatic player in a longer, more complicated story of decline? These are the questions we'll explore tonight, slowly and carefully. We'll look at the evidence for impact. We'll examine the volcanic hypothesis. We'll consider climate change, sea level fluctuations, and ecological cascades. We'll meet the scientists who have dedicated their lives to understanding those few centimetres of clay, and perhaps most importantly, we'll come to understand why, after all these decades of research, we still can't say with absolute certainty what killed the dinosaurs. There's something beautiful in that uncertainty, I think. It reminds us that the past, even the deep past, isn't static. It's not a fixed story we can simply read. It's something we reconstruct, interpret, debate. Every new fossil, every new rock analysis, every new computer model adds another piece to an impossibly complex puzzle. And that brings us to where we need to begin, with the evidence itself, with the thin layer of clay that started it all. Picture a cliff face in Colorado, or a road cut in Italy, or a canyon wall in New Mexico. The rock is sedimentary, layer upon layer of ancient seafloor or river deposits. Each stratum a page in Earth's diary. Most of the layers blend into each other, subtle gradations marking the passage of time. But then there's a line, thin, dark, distinct. Below it, the rock is full of fossils, ammonites, marine reptiles, pollen from flowering plants, and yes, dinosaur bones in the terrestrial deposits. Above it, many of those fossils simply aren't there anymore. This is the KPG boundary, named for the two geological periods it separates, Cretaceous and Paleogene. The K comes from the German word for Cretaceous, Krede. It's found on every continent in marine and terrestrial deposits alike. Sometimes it's barely visible, just a subtle change in rock colour. Sometimes it's dramatic, a clear demarcation between two different worlds. When Luis and Walter Alvarez began studying this boundary layer in the late 1970s, they were trying to answer a straightforward question. How long did the extinction take? They thought they could use the iridium in the clay as a kind of clock. Iridium falls to Earth constantly in cosmic dust, at a steady, measurable rate. By calculating how much iridium was in the boundary layer, they could estimate how many years it represented. But when they analysed the clay, they found something shocking. The iridium levels weren't just slightly elevated. They were 30 times higher than normal, sometimes more. That much iridium couldn't have accumulated slowly over thousands of years. It must have arrived all at once, in a single catastrophic event, and the only plausible source was an asteroid or comet, perhaps 10 kilometres across, striking Earth at speeds that are difficult to comprehend. The Alvarez hypothesis, published in 1980, proposed that this impact created a global catastrophe. The asteroid would have vaporized on contact, sending billions of tons of debris into the atmosphere. The impact itself would have caused earthquakes of unimaginable magnitude, tsunamis that crossed entire oceans, wildfires sparked by falling ejecta. But the real killer would have been the dust. So much material thrown into the stratosphere that it blocked out the sun for months. Perhaps years. Photosynthesis would have stopped. Plants would have died. Herbivores would have starved. Carnivores would have followed. The entire food chain would have collapsed. It was an elegant, terrible explanation, and it was immediately controversial. Many paleontologists rejected it outright. The fossil record, they argued, showed a more gradual decline. Dinosaurs had been struggling for millions of years before the boundary. Some groups had already gone extinct. The impact theory seemed too simple, too sudden, too clean. It felt like physics imposing itself on biology, an extraterrestrial deus ex machina solving a problem that might have more complex, more terrestrial causes. But the iridium was real. The worldwide distribution of the boundary layer was real, and as scientists looked closer, they found more evidence: shocked quartz, a type of mineral that only forms under the extreme pressures of impact or nuclear explosion. Tektites, tiny glass spheres created when molten rock is thrown into the atmosphere and cools as it falls. Soot, suggesting global wildfires. All of it consistent with a massive impact. The question became, where? If an asteroid 10 kilometers across had struck Earth, it would have left a crater nearly 200 kilometers in diameter. Where was it? For years, this was the missing piece of the puzzle. Impact proponents searched for the smoking gun, the crater that would prove their case beyond doubt. And in 1991, they found it. Or rather, they confirmed what Mexican petroleum geologists had discovered decades earlier but hadn't recognized. The Chicxulub crater, buried beneath the Yucatan Peninsula and the Gulf of Mexico. 150 kilometers wide, 66 million years old, exactly the right age, exactly the right size, the impact site. With that discovery, the impact theory gained tremendous strength. But it didn't end the debate, because by then scientists had discovered something else, something that complicated the simple narrative of asteroid-caused extinction. And it's this complication, this additional layer of evidence, that leads us to consider what else was happening at the end of the Cretaceous. While the Alvarez team was studying iridium in Italy, geologists on the other side of the world were documenting something equally dramatic. In west-central India, covering an area larger than France, lay a vast plateau of volcanic rock. Not the remains of a single volcano, but the accumulated outpourings of countless eruptions, layer upon layer of basalt stacked more than 2 kilometers thick in places. They called it the Deccan traps, from the Sanskrit word for stairs, describing the step-like landscape the eroded lava flows created. Volcanic provinces like this exist in several places on Earth. The Columbia River basalts in the Pacific Northwest, the Siberian traps, the Central Atlantic Magmatic Province. They're called large igneous provinces, or LIPs, and they represent volcanism on a scale that makes even the most violent modern eruptions look trivial. We're not talking about a mountain blowing its top. We're talking about the Earth's crust rupturing, about magma pouring out of fissures that stretched for hundreds of kilometers, about eruptions that continued not for days or weeks, but for hundreds of thousands of years. The Deccan traps were one of these provinces, and when geologists dated the rocks, they discovered something remarkable. The main pulse of eruptions occurred right around 66 million years ago, right around the KPG boundary, right around the time the dinosaurs died. This wasn't the slow, gentle volcanism of Hawaii, building islands one flow at a time. This was catastrophic. Individual eruptions could have released enough lava to bury the entire state of Texas under 10 meters of molten rock. And these eruptions happened repeatedly, in pulses, for perhaps 500,000 years before the boundary, and continuing for another 500,000 years after. The total volume of lava would eventually cover an area larger than Western Europe, but lava itself wouldn't have caused global extinction. The danger lay in what the eruptions released into the atmosphere. Each eruption belched enormous quantities of sulfur dioxide and carbon dioxide into the air. Sulfur dioxide combines with water vapor to create sulfuric acid, which falls as acid rain and creates a cooling effect by reflecting sunlight back into space. Carbon dioxide is a greenhouse gas, causing warming. The Deccan eruptions would have swung the climate wildly between cooling and warming phases, disrupting ecosystems, stressing species, making survival difficult even for animals that had thrived for millions of years. There's evidence of this stress in the fossil record. In the millions of years before the KPG boundary, dinosaur diversity seems to have been declining in some regions, though this remains hotly debated. Some species were thriving, particularly in Asia and North America. Others were struggling. The climate was changing. The continents were drifting into new configurations, altering ocean currents and weather patterns. And all the while, the Deccan was erupting, adding its poisonous gases to an atmosphere already in flux. Some scientists began to argue that the Deccan volcanism, not the asteroid, was the primary cause of the extinction. The impact, they suggested, was just bad luck, a final blow to ecosystems already on the brink. Others proposed that the impact might have triggered increased volcanic activity, that the seismic waves from Chicxulub could have caused fresh eruptions on the other side of the planet. Still others wondered if the volcanism had weakened the biosphere, making it more vulnerable to impact. The timing seemed almost too coincidental to ignore. The largest impact crater of the past 100 million years, and the largest volcanic eruption of the past 100 million years, occurring within perhaps a few 100,000 years of each other, both around the time of the largest mass extinction since the end Permian event 252 million years ago. Was it just chance, or was there a connection we don't yet understand? This is where the story gets complicated, where simple explanations start to fray. Because nature doesn't usually work in simple ways. Systems interact, causes overlap. What looks like a single catastrophe from 66 million years in the future might have been a cascade of interconnected disasters, each amplifying the others, creating conditions where even the mighty dinosaurs, survivors of so many earlier crises, could not adapt quickly enough. And this brings us to something we need to examine more closely. What exactly happens in the moments and months and years after such catastrophes, and how that might tell us which one, if either, was truly responsible for the end of the dinosaurs? Let's slow down for a moment and truly contemplate what these events would have meant in physical terms, not as abstractions, not as numbers on a page, but as actual experiences for the planet and everything living on it. An asteroid 10 kilometers across, traveling at perhaps 20 kilometers per second, strikes the shallow sea off what will one day be Mexico's Yucatan Peninsula. The energy released is equivalent to 100 million megatons of TNT. That's more than 1 billion times the energy of the atomic bomb dropped on Hiroshima. In the first second, the asteroid and the rock beneath it simply cease to exist as solids. They vaporize. Temperatures reach tens of thousands of degrees. A crater begins to form, punching through the Earth's crust, creating a cavity nearly 30 kilometers deep before the rock rebounds, in a process that takes just minutes. The shock wave radiates outward at supersonic speeds. Trees are flattened for hundreds of kilometers in all directions. The impact occurs in water, so unimaginable quantities of seawater are vaporized, thrown into the atmosphere, or pushed outward in a wave that grows as it travels. Near the impact site, the tsunami might be a kilometer high. When it reaches distant shores, it's still tens or hundreds of meters tall, powerful enough to sweep across coastal lowlands, drowning entire ecosystems in a matter of hours. But that's just the beginning. The vaporized rock, mixed with the remains of the asteroid, doesn't simply disappear. It rises into the atmosphere on a column of superheated gas, reaching altitudes where it begins to spread across the globe. Some of this material is moving fast enough to achieve escape velocity, actually leaving Earth's atmosphere altogether before falling back. As it re-enters, it heats up through friction with the air, glowing red hot, thousands upon thousands of tons of molten rock and metal raining down across the entire planet. Forests ignite, not just near the impact site, but everywhere. The radiant heat from billions of particles burning up in the atmosphere is enough to cause spontaneous combustion of dry vegetation worldwide. Within hours, massive wildfires are burning on multiple continents. The sky glows orange. Smoke begins to add to the debris already filling the atmosphere, and then comes the darkness. The dust and soot and ash create a global shroud. How dark it gets, and for how long, remains one of the great uncertainties. Some models suggest near total darkness for several months. Others propose a dimming to perhaps 10% of normal sunlight, lasting for a year or two. Either way, the effect on photosynthesis is catastrophic. Plants die. Herbivores starve. The food chain collapses from the bottom up. Now consider the volcanic alternative. The eruptions don't happen all at once, but they're persistent. A fissure opens in what will become India. Lava flows out at temperatures exceeding 1000 degrees Celsius. It flows for months, perhaps years, covering thousands of square kilometers. The lava itself buries ecosystems, but again, the real danger is atmospheric. Sulfur dioxide creates acid rain. Oceans acidify, killing marine organisms that form the base of oceanic food webs. The cooling effect of sulfate aerosols in the atmosphere might drop global temperatures by several degrees, but then the sulfates fall out, washed from the air by the very acid rain they helped create. And the carbon dioxide they were masking begins to assert itself. Temperatures rise, the climate whipsaws between states. Species adapted to stability struggle to survive. The stress is chronic rather than acute. Not one terrible day, but thousands of terrible years. Ecosystems don't collapse all at once. They fray, unravel, lose complexity. Large animals requiring extensive territories and substantial food supplies find their world shrinking. Reproduction rates fall. Populations fragment. And when a population of large animals becomes too small, too isolated, it enters what biologists call an extinction vortex, a spiral from which recovery becomes statistically unlikely. Which scenario is worse? Which would cause the extinction pattern we see in the fossil record? The honest answer is that we're not entirely sure. Both catastrophes are beyond human experience. We have no perfect analogues, no experiments we can run. We can only model, simulate, extrapolate from what we know about smaller impacts, historical volcanic eruptions, modern ecosystem collapse. And this uncertainty, this gap between what we can theorize and what we can prove, is central to understanding why we still don't know exactly what killed the dinosaurs. The evidence exists, but interpreting it requires making assumptions, and different assumptions lead to different conclusions. If we want to know what killed the dinosaurs, the most obvious place to look is at the dinosaurs themselves, their bones, their eggs, their footprints. The fossil record should tell us whether they died suddenly or gradually, whether all groups suffered equally, or some were more vulnerable than others. But the fossil record is not a simple chronicle. It's fragmentary, biased, difficult to interpret. Fossilization is rare. It requires specific conditions, rapid burial, the right chemistry, the right geology. Most organisms that die simply decay, their molecules recycled by bacteria and fungi, their forms lost to time. Only a tiny fraction of the dinosaurs that ever lived left fossils, and only a fraction of those fossils have been found. This creates what paleontologists call the senior lips effect, named for two scientists who formalized the concept in 1982. Essentially, it states that the last fossil of a species is almost never the last individual of that species. There's a gap, sometimes a large gap, between when a species actually goes extinct and when we find its last fossil. This makes it difficult to determine whether extinctions were sudden or gradual. Look at the late Cretaceous formations in Montana, or Alberta, or Mongolia. In the layers just below the KPG boundary, we find dinosaurs, Tyrannosaurus, Triceratops, Edmontosaurus, dozens of species. But the very last layer before the boundary? Sometimes there are no dinosaur fossils at all in the final few meters. Does that mean dinosaurs had already disappeared before the impact or eruptions? Or does it simply mean we haven't found fossils from those last days? Some paleontologists have argued that dinosaur diversity was declining long before the KPG boundary. They point to studies showing fewer species in the latest Cretaceous, evidence of ecological stress, indications that the dinosaurs were already on their way out. The asteroid, or volcanism, in this view, simply finished a process already underway. Others argue that these patterns are artifacts of preservation and sampling. North American fossil sites are excellent, but they represent only one region. In Asia, dinosaurs seem to have been thriving right up to the boundary. Different continents, different stories, and the statistical methods used to assess diversity are complex, dependent on assumptions that may or may not be valid. There's also the question of ecological position. Large animals often go extinct first in times of environmental stress. They need more food, larger territories, and they reproduce more slowly. Dinosaurs were, on average, enormous compared to mammals. The smallest adult tyrannosaurs weighed more than most modern land predators. Herbivores like sauropods could reach weights of 30 or 40 metric tons. Size might have been a liability. But then why did some large animals survive? Crocodiles made it through. They're large, and they haven't changed much in the 66 million years since. Turtles survived. Many fish. Birds, which are literally small dinosaurs, not only survived but diversified. The pattern isn't as simple as quote zero. There's something more subtle at work, something about ecological niche, about adaptability, about what kinds of stress an organism could withstand. Marine reptiles offer another perspective. Mosasaurs were dominant ocean predators, some reaching lengths of 15 meters. Plesiosaurs, including the long-necked elasmosaurs, were successful for over 100 million years. All of them disappeared at the KPG boundary, but for different reasons than the dinosaurs. Marine ecosystems were disrupted in specific ways, particularly if an impact in shallow water created massive tsunamis and debris falls, or if volcanic gases acidified the oceans. The ammonites, shelled cephalopods that had survived multiple earlier extinctions, finally went extinct too. But their relatives, the nautiloids, survived and still exist today. Why? What made nautiloids more resilient? Was it their habitat depth, their diet, their reproductive strategy? We don't know, not with certainty. Every piece of evidence seems to suggest a different story, or at least a different emphasis. The fossil record tells us there was a major extinction. It tells us the extinction was sharp, probably occurring over a timescale of thousands of years rather than millions. But it doesn't clearly distinguish between a world killed by impact and a world killed by volcanism, or by both, or by something else entirely. And so we're forced to look at other types of evidence, other ways of reading what happened, which leads us deeper into the geological record, into the chemistry preserved in rocks, into the subtle signals left by environmental change. Rocks remember, not in the way living things remember, but through chemistry, through the ratios of elements and isotopes locked into minerals as they form. These chemical signatures can reveal ancient temperatures, atmospheric composition, ocean chemistry, even the presence of life. At the KPG boundary, rocks from around the world preserve a chemical record of catastrophe. Consider carbon isotopes. Carbon comes in different forms, or isotopes, primarily carbon-12 and carbon-13. Living things preferentially use carbon-12 in photosynthesis, so organic matter is enriched in this lighter isotope. When paleontologists measure the ratio of carbon-13 to carbon-12 in ancient rocks, they can estimate how much biological productivity was occurring when those rocks formed. At the KPG boundary, there's a distinctive shift in carbon isotopes. The ratio changes abruptly, suggesting a sudden decrease in photosynthesis. Plant life crashed. The change is global, found in marine and terrestrial deposits alike. It's exactly what you'd expect if something blocked out the sun, stopping photosynthesis worldwide. Point to the impact team, it would seem. But there's complexity here. The carbon isotope excursion, as it's called, doesn't happen instantaneously at the boundary. In some locations it begins slightly before, in others it peaks after. The signal is noisy, complicated by variations in local deposition rates and preservation. And massive volcanic eruptions also affect carbon isotope ratios through the release of carbon dioxide from the mantle, through changes in ocean chemistry, through acid rain's effects on terrestrial ecosystems. Oxygen isotopes tell a different story, about temperature and precipitation. The ratio of oxygen-18 to oxygen-16 in fossilized shells and minerals reveals how warm or cold the ocean was when the organism lived. Studies of oxygen isotopes across the KPG boundary show temperature fluctuations in the final million years of the Cretaceous. The climate was already unstable, swinging between warmer and cooler phases. This instability might have been caused by Deccan volcanism, or it might have been part of longer-term geological cycles. Then there's sulfur. Sulfur isotopes can reveal the presence of massive releases of volcanic gases. At the KPG boundary, some studies have found sulfur anomalies consistent with intense volcanism, but distinguishing volcanic sulfur from impact-generated sulfur is difficult. The Chicxulub impact occurred in a region with sulfate-rich rocks. The impact would have vaporized these deposits, sending sulfur into the atmosphere in quantities comparable to volcanic eruptions. Osmium isotopes offer another angle. Osmium, like iridium, is rare in Earth's crust, but more common in asteroids and in the mantle. The ratio of different osmium isotopes can distinguish between extraterrestrial osmium, from an asteroid, and mantle osmium, from volcanic eruptions. Studies have found both signatures at the KPG boundary. Extraterrestrial osmium from the impact. Mantle osmium from the Deccan eruptions. Both catastrophes left their marks. Mercury is a newer line of evidence. Volcanic eruptions release enormous amounts of mercury into the environment. Recent studies have found mercury spikes in KPG boundary sediments, suggesting intense volcanic activity right around the time of the extinction. But again, the timing is debated. Some mercury anomalies occur before the impact, others occur after. The Deccan eruptions weren't a single event, but a series of eruptions over hundreds of thousands of years, each potentially leaving its own mercury signature. What we're seeing in all this chemical evidence is not a simple story, but a layered one. The iridium anomaly is real and global, strong evidence for an asteroid impact. The shocked quartz, the tektites, the Chicxulub crater itself, all confirm that an impact occurred. But the other chemical signals, the carbon and oxygen and sulfur and mercury, they tell a more complex tale. They suggest environmental stress before the impact, temperature fluctuations, ecosystem disruption, the kind of chronic pressure that might have made life more vulnerable when the acute crisis of impact arrived. It's like trying to determine cause of death in a patient with multiple conditions. Did the patient die of the sudden heart attack, or of the underlying heart disease that made the attack fatal, or of the lung disease that complicated recovery, or of all of them together? The chemical evidence shows us that the end Cretaceous Earth was sick in multiple ways, stressed by multiple factors. Determining which one delivered the final blow, or whether it was the combination, remains challenging, and this complexity only deepens when we look at the physical evidence of impact, at what the Chicxulub crater itself reveals about that terrible day. The Chicxulub crater is buried. Most of it lies beneath a kilometre or more of younger sediments, hidden under the jungles of the Yucatan and the warm waters of the Gulf of Mexico. You can't see it from the surface. There's no dramatic depression, no obvious scar. The landscape has healed, filled in, moved on, but beneath that surface the crater remains, a frozen record of violence. In the 1990s and 2000s, scientists drilled into the crater, extracting cores of rock that tell the story of impact. The cores show the structure, a central peak ring, where rock rebounded upward after the initial compression, surrounded by terraced walls, surrounded by an outer rim. The entire structure is about 150 kilometers across, though some of the effects extend much farther. The rocks themselves are transformed. Beneath the crater lies a layer of impact melt, rock that was literally melted by the energy of collision and then cooled into glass. Below that are breccias, shattered and jumbled rocks, pieces of the target area mixed with pieces of the asteroid. Some of these rocks contain shocked quartz, with distinctive microscopic structures that can only form under the extreme pressures of impact or nuclear explosion. Dating these rocks is crucial. If the impact really killed the dinosaurs, it needs to be the right age, needs to line up precisely with the KPG boundary, and it does. Multiple dating methods, using different radioactive isotopes, all converge on the same age. 66 million years, with an uncertainty of only a few tens of thousands of years. Geologically speaking, it's a perfect match. But the crater also reveals something interesting about the impact itself. The asteroid hit at an angle, striking from the northeast at about 60 degrees from horizontal. This matters because an oblique impact is more efficient at throwing debris into the atmosphere than a straight-down impact. More ejecta means more global distribution of material, more blocking of sunlight, more soot from global wildfires. The angle of impact might have made the catastrophe worse. There's also the question of what the asteroid hit. The Yucatan Peninsula in the late Cretaceous was a shallow carbonate platform, rich in limestone and gypsum. Limestone is calcium carbonate. Gypsum is calcium sulfate. When you vaporize these rocks, you release enormous amounts of carbon dioxide and sulfur dioxide. The carbon dioxide contributes to greenhouse warming. The sulfur dioxide creates sulfate aerosols that cool the planet and create acid rain. The impact didn't just release energy, it released chemistry. Some estimates suggest the Chicxulub impact could have released more sulfur into the atmosphere than a decade of Deccan eruptions, all in a single day. The immediate cooling from sulfate aerosols would have been severe, potentially dropping global temperatures by 10 degrees Celsius or more within weeks. The darkness from dust and soot would have compounded the effect. And then, as the aerosols washed out over the following years, the carbon dioxide would assert itself, causing rapid warming. This kind of rapid, extreme climate whiplash would be devastating to ecosystems. Species adapted to Cretaceous warmth would suffer in the sudden freeze. But they wouldn't have time to adapt before the warming hit. It's the speed of change, as much as the magnitude, that causes extinction. Drilling into the crater has also revealed something about the immediate aftermath. Above the impact melt and breccia, there's a layer of sediment that accumulated in the hours and days after impact. It contains the fossils of organisms that lived in the impact winter, in the strange, dark world that followed the collision. Most of these fossils are of bacteria and simple organisms. Complex life was struggling or absent. But here's where interpretation becomes difficult. The crater tells us about the impact event itself, about the energy released, about the materials involved. It doesn't directly tell us what happened globally, how long the darkness lasted, how severe the cooling was, how many species went extinct immediately versus those that lingered for years or decades. For that, we need evidence from further afield, from the boundary layer deposits found around the world. And when we look at those deposits, we find something puzzling. The evidence for global wildfire is strong in some locations, weak in others. The evidence for extended darkness is harder to pin down than early models suggested. The extinction pattern is complex, with some groups dying out rapidly and others declining more gradually. Which brings us back to the question of volcanism, and whether the Deccan eruptions might have played a larger role than the impact narrative usually allows. If you could visit the Deccan traps today, you'd see a landscape of rolling plateaus, weathered cliffs. Ancient lava flows eroded into dramatic shapes by 66 million years of rain and wind. The rock is dark basalt, iron-rich and heavy. In places you can see the distinct layers of individual flows, stacked like a geological layer cake. Each layer represents a separate eruption, a separate outpouring of lava from the mantle below. The sheer volume of rock is difficult to comprehend. Estimates suggest the Deccan eruptions produced more than 500,000 cubic kilometers of lava. To put that in perspective, if you spread that lava evenly across the entire United States, it would create a layer more than 50 meters thick. And this is just what remains. Much of the original lava has been eroded away over millions of years. The original volume might have been twice as large. But it's not the lava that would have caused extinction, it's the gas. Every time magma rises from the mantle and erupts onto the surface, it releases dissolved gases, primarily carbon dioxide and sulfur dioxide. For normal volcanic eruptions, this is a local problem. The gases disperse, are absorbed by the ocean and vegetation, or washed out by rain. The planet can handle it. But the Deccan wasn't normal. The eruptions were enormous, sustained, and they happened during a period of perhaps 1,000,000 years, with the most intense activity concentrated in a few 100,000 years around the KPG boundary. Recent research has tried to refine the timing of Deccan eruptions using improved dating techniques. What they've found is that the main pulses of activity occurred in distinct phases. There was a phase before the Chicxulub impact. There was intensified activity right around the time of impact, and there was continued eruption for hundreds of thousands of years after. This pulsed activity would have created periods of severe environmental stress, separated by periods of relative recovery, preventing ecosystems from fully stabilizing. Climate modelling suggests that Deccan eruptions could have caused global temperature swings of several degrees Celsius. Sulfur dioxide would cause initial cooling and acid rain. But sulfur washes out of the atmosphere in just a few years. The carbon dioxide lingers, accumulating over time, causing gradual warming. The planet would have oscillated between cooler and warmer states, with acidified oceans, disrupted rainfall patterns, and stressed ecosystems. Evidence for this stress appears in the fossil record. Marine microfossils show significant turnover in the 1,000,000 years before the KPG boundary. Plankton species that had been stable for millions of years began to disappear, replaced by different species more tolerant of changing conditions. On land, pollen records show shifts in plant communities, suggesting climate change and possible ecosystem reorganization. Some researchers argue that these changes indicate the dinosaurs were already in decline before the asteroid hit. The Deccan eruptions had been weakening the biosphere for hundreds of thousands of years. Large animals, which are always more vulnerable to environmental stress, were struggling. The asteroid impact simply finished what volcanism had started. Others point out that similar volcanic episodes earlier in Earth's history didn't cause mass extinctions. The Columbia River basalts, the Krufara eruptions, these were massive igneous provinces that erupted without wiping out most of life on Earth. What made the Deccan different? Perhaps nothing. Perhaps volcanism alone wasn't enough to cause mass extinction. Perhaps it required the additional stress of a massive impact to push ecosystems over the edge. There's even a hypothesis that the impact might have intensified the Deccan eruptions. The seismic waves from Chicxulub would have circled the Earth, converging on the opposite side of the planet with enough force to potentially trigger earthquakes and volcanic eruptions. The Deccan traps aren't exactly opposite Chicxulub, but they're close. Could the impact have caused a fresh pulse of eruptions? Some scientists think it's possible, others are skeptical, noting that seismic waves, even from the largest earthquakes, don't usually trigger distant volcanic activity. What we're left with is a picture of dual catastrophes, asteroid and volcano, occurring close enough in time that their effects overlapped, interacted, possibly amplified each other. Separating their individual contributions to the extinction is perhaps impossible without a time machine. The best we can do is model, simulate, and compare the predicted effects with the geological and paleontological evidence. And that evidence, as we'll see, contains some surprising patterns that complicate both the impact and volcanic hypotheses. Extinction is a selective process. It doesn't take everything equally. Some groups are more vulnerable than others, and understanding why certain organisms went extinct while others survived can tell us something about the nature of the catastrophe that caused the extinction. At the KPG boundary, the pattern of survival is fascinating and complex. In the oceans, the ammonites disappeared entirely. These were abundant, diverse, successful cephalopods that had survived multiple earlier extinction events. But their close relatives, as the nautiloids, made it through. Both were shelled cephalopods, both lived in similar environments. Why did one group die out while the other persisted? One hypothesis focuses on reproductive strategy. Ammonites laid numerous small eggs and had short lifespans, often just a year or two. They were fast-living, fast-reproducing, adapted to stable environments. Nautiloids laid fewer, larger eggs and lived longer, sometimes decades. In a catastrophically disrupted ocean, perhaps the slow and steady strategy worked better than the fast and fragile one. Marine reptiles disappeared completely. mosasaurs, plesiosaurs, sea turtles larger than cars, all gone. But crocodiles, which also lived in marine and coastal environments, survived. Sea turtles survived, though barely. The difference might be ecological. Marine reptiles were apex predators or specialized feeders, dependent on complex food webs. When those food webs collapsed, they had nowhere to turn. Crocodiles are generalists, able to eat almost anything, able to go long periods without food. That flexibility might have saved them. On land, the pattern is even more intriguing. All non-avian dinosaurs disappeared. But birds, which are avian dinosaurs, survived. Not all birds. Many lineages went extinct, but some made it through. And these survivors gave rise to all modern bird diversity. What made these particular birds special? They were generally small. They could fly, allowing them to search widely for food, and many of them had beaks adapted for eating seeds. Seeds are crucial. When the impact or volcanism killed off most plant life, seeds remained in the soil, dormant but viable. A seed-eating bird could survive on this reserve even when fresh plant growth was impossible. Insect-eating birds, which depended on active ecosystems, fared poorly. Carnivorous birds that needed other animals to be healthy and available went extinct, but seed-eaters held on, waiting for the world to green again. Mammals also survived, and their survival offers clues. Late Cretaceous mammals were mostly small, shrew-like animals, many of them nocturnal or burrowing. They were generalists, eating insects, plants, perhaps small vertebrates. They didn't need extensive territories or large amounts of food. When plants died back, they could survive on seeds, roots, insects, carrion. Their small size meant they needed less food overall. Their burrowing habits might have protected them from the initial heat pulse if the impact caused global fires. But not all small animals survived. Many small dinosaurs went extinct along with their larger relatives. Size wasn't the only factor. Ecological niche mattered. Adaptability mattered. The ability to find food in a drastically altered world mattered. Plants show an interesting pattern too. In the northern hemisphere, there's evidence of widespread plant extinction, with fern spores becoming suddenly abundant in the boundary layer. This fern spike suggests that after the catastrophe, ferns, which reproduce by spores and can colonize disturbed ground quickly, took over from flowering plants and conifers. It's a sign of ecological devastation followed by opportunistic recovery. But in the southern hemisphere, the plant extinction seems less severe. Some regions show continuity of flora across the boundary. This could be because the impact and its immediate effects were more severe in the northern hemisphere, or because different plant communities had different vulnerabilities, or because preservation biases are affecting what we see in the fossil record. Freshwater ecosystems also showed resilience. Freshwater fish, crocodiles, turtles, amphibians, they mostly survived. Freshwater environments might have been buffered from some of the worst effects. Rivers and lakes collect sediment and organic material, potentially providing food even when primary productivity crashed. And freshwater organisms are often adapted to variable conditions, to seasonal floods and droughts, to changing temperatures. That adaptability might have helped. What all these patterns suggest is that the KPG extinction wasn't random. It selected for certain traits: small size, generalist diet, ability to survive on stored resources like seeds or buried organic matter, tolerance for variable conditions. It selected against specialization, large body size, dependence on complex ecosystems, and need for stable conditions. And these patterns constrain what the killing mechanism could have been. Scientists can't rerun the end Cretaceous extinction to see what happens. They can't drop an asteroid on modern Earth, or trigger massive volcanic eruptions to test hypotheses. What they can do is build computer models, mathematical simulations of climate, atmosphere, oceans, and ecosystems, and see what those models predict for different catastrophe scenarios. Climate modelling has become increasingly sophisticated over the past few decades. Modern models can simulate atmospheric chemistry, ocean circulation, temperature distribution, precipitation patterns. They can account for the effects of asteroid-generated dust, volcanic aerosols, greenhouse gases, changes in solar radiation, and they can run these simulations for the late Cretaceous Earth, with its different continental positions, different ocean currents, different baseline climate. Early impact models suggested a scenario of near-total darkness lasting for months. The dust and soot from the impact and global wildfires would block out virtually all sunlight, causing photosynthesis to cease completely. Temperatures would plunge, the entire planet would freeze. It was called impact winter, analogous to the nuclear winter scenario developed during the Cold War. But more recent, more detailed models have complicated this picture. The amount of dust injected into the stratosphere depends on the impact angle, the composition of the target rocks, the size of the asteroid. Too much uncertainty in these parameters means the darkness scenario remains uncertain. Some models suggest substantial but not complete blocking of sunlight, perhaps reducing light levels to 10% of normal rather than near zero. Photosynthesis would be severely impacted but not entirely stopped. The duration of darkness is also debated. Particles don't stay suspended in the atmosphere indefinitely. They fall out, are washed out by rain. Some models suggest the atmosphere might have cleared substantially within weeks to months. Others predict longer darkness. A year or more, the difference matters enormously for ecosystems. A few months of darkness is catastrophic but survivable for some species. A year or more is extinction level for most complex life. Volcanic models face similar uncertainties. How much gas did each eruption release? How long did individual eruptions last? How are the gases distributed in the atmosphere? Sulfur dioxide creates cooling, but it also creates acid rain that helps remove the sulfur from the atmosphere. Carbon dioxide accumulates, causing warming, but the oceans absorb some of it, creating acidification. The interactions are complex, non-linear. What volcanic models do consistently show is climate instability. Repeated pulses of eruptions would have caused repeated swings in temperature and ocean chemistry. Ecosystems wouldn't have time to stabilize between disturbances. This chronic stress might have been more damaging than a single acute event because it prevented recovery, kept populations small and vulnerable, eroded resilience over time. Some recent models have tried to simulate both factors together. Deccan volcanism weakening the biosphere over hundreds of thousands of years, then the Chicxulub impact delivering the final blow. These combined models show effects that are worse than either catastrophe alone. The volcanism creates chronic stress. The impact creates acute crisis. Together they create conditions where recovery becomes almost impossible. But models have limitations. They're only as good as their inputs, and many of the inputs for the late Cretaceous are uncertain. We don't know exactly what the atmosphere was like. We don't know the precise distribution of vegetation or ocean temperatures. We're working with estimates, educated guesses, extrapolations from limited data. Small changes in initial conditions can sometimes produce large changes in outcomes. There's also the challenge of modelling ecosystems and biology. Climate models can tell us about temperature and precipitation, but how do those changes translate into species extinction? An organism doesn't die just because temperature drops 10 degrees. It dies because it can't find food, or can't reproduce, or can't compete with other species that are better adapted to the new conditions. Modelling these biological responses is incredibly difficult. Some researchers have tried ecosystem modelling, creating simplified representations of food webs and seeing how they respond to environmental shocks. These models generally confirm what we'd expect. Large animals at the top of food chains are most vulnerable. Generalists survive better than specialists, and rapid environmental change is more deadly than gradual change. What we learn from models is that both impact and volcanism are capable of causing mass extinction. The physical mechanisms exist. The climate effects would have been severe, but pinning down exactly what happened with certainty remains elusive. Models show what could have happened, not necessarily what did happen. And this is where we need to turn to another line of evidence, one that's only recently become available: the ability to look at the extinction event in extremely fine time resolution, year by year, sometimes even season by season. Some organisms keep diaries, not intentional records, but growth patterns that reveal the passage of time with remarkable precision. Trees are the most familiar example, adding a ring of wood each year, but the ocean has its own record keepers: mollusk shells, fish otoliths, corals, and these records can sometimes survive as fossils, preserving information about seasonality, about growth rates, about environmental conditions millions of years in the past. Researchers studying the KPG boundary have recently begun analysing fossil shells with unprecedented detail, looking at the chemistry and structure at microscopic scales. What they've found is fascinating. Some shells from the latest Cretaceous, from the final years before the extinction, show growth patterns consistent with severe environmental stress. The animals that made these shells were struggling, growing slowly, experiencing conditions outside their normal range. One particularly revealing study looked at ammonite shells from the final 100,000 years of the Cretaceous. The shells showed evidence of temperature fluctuations, with cooler and warmer periods alternating. This is consistent with volcanic climate forcing, with pulses of Deccan eruptions causing repeated environmental disruptions. The ammonites survived these disruptions, but their growth was affected, their populations perhaps weakened. Then comes the boundary itself, and the evidence changes. In some locations there are fossils from the days and weeks immediately after the impact. Fish killed by the tsunami, their bodies buried in impact debris. Shells with growth lines that simply stop, recording the moment when the organism died. These are among the most precise glimpses we have of the extinction event itself. One remarkable site is Tanis in North Dakota, a fossil deposit that might preserve the very day of the Chicxulub impact. The site contains fish with impact spherules, tiny glass beads from the impact lodged in their gills. These fish apparently died within hours of the impact, asphyxiated by debris falling from the sky. If the interpretation is correct and not all paleontologists are convinced, then Tanis is a frozen moment, a snapshot of catastrophe. The fish bones at Tanis show growth rings. By analysing these rings, researchers can estimate how old the fish were, what season they died in. The initial analysis suggested they died in spring or early summer in the Northern Hemisphere, an interesting detail, though perhaps not critical to understanding the overall extinction. Still, it illustrates the level of detail that's now possible. Other studies have looked at shell chemistry, at the ratios of elements incorporated into the calcium carbonate as the shell grows. Oxygen isotopes reveal water temperature, magnesium reveals metabolic stress, carbon reveals food availability. A single fossil shell, if well preserved, can be a multi-proxy record of environmental conditions. What these studies are revealing is variability. Conditions weren't uniform across the planet or even within a single region. Some organisms show stress before the boundary. Others seem fine until the very end. Some locations show evidence of rapid environmental change. Others show more gradual shifts. It's a mosaic, a complex picture that doesn't reduce easily to a simple narrative. This variability matters for understanding what killed the dinosaurs. If the extinction was caused solely by the Chicxulub impact, we'd expect a sharp, globally synchronous event. Organisms should look healthy until the impact, then die rapidly. If the extinction was caused by Deccan volcanism, we'd expect a more gradual pattern, with increasing stress leading up to the boundary. What we actually see is something in between. There's evidence of pre-boundary stress in some locations and lineages. There's evidence of catastrophic disruption right at the boundary. And there's evidence of prolonged recovery afterward, with ecosystems taking hundreds of thousands of years to fully stabilize. It suggests a multi-phase extinction, with volcanism creating vulnerability and impact delivering the final blow. But there are complications. dating uncertainty means we can't always tell whether something happened 1,000 years before the boundary or 1,000 years after. Preservation bias means we have better records from some places and some types of organisms than others, and biological variability means that even organisms experiencing the same environmental conditions might respond differently. Still, the trend in research is clear. Higher resolution data, better analytical techniques, more precise measurements. We're getting closer to understanding the sequence of events, the timing of different factors, the progression of extinction. But closer doesn't mean certain, and the picture remains incomplete. Which brings us to a key question. Can we determine from geological evidence how quickly the extinction occurred? How long does it take for a world to end? For 75% of species to disappear? For ecosystems that have been stable for millions of years to collapse? The answer matters because it constrains the possible causes. A truly instantaneous extinction, occurring in days or months, points strongly toward impact. A gradual extinction, spanning thousands or tens of thousands of years, might be better explained by volcanism or climate change. The challenge is measuring time at these scales. Geological dating methods like radiometric dating can tell us the age of a rock to within tens or hundreds of thousands of years, sometimes better. That's impressively precise for rocks tens of millions of years old. But it's not precise enough to distinguish between an extinction that took a year and one that took 10,000 years. Both would look instantaneous on a geological timescale, so researchers have developed indirect methods for assessing extinction speed. One approach looks at the thickness of the boundary layer. If the clay that contains the iridium and other impact signatures represents a short period of time, then the extinction was rapid. If it represents a longer period, then perhaps the extinction was more drawn out. Sediment accumulation rates are tricky to estimate, but in some deep-sea cores, where deposition is slow and steady, researchers can make reasonable estimates. The boundary layer in these locations is often just a few centimeters thick. At typical deep-sea accumulation rates, a few centimeters might represent anywhere from a few hundred to a few thousand years. Not instantaneous on human timescales, but very rapid geologically. On land, the picture is different. Terrestrial sediment deposition is much more variable, with floods and droughts and changing river courses creating complicated layer patterns. In many locations, there are gaps in the record right around the KPG boundary, periods where no sediment was deposited or where sediment was deposited and then eroded away. These gaps make it difficult to assess timing. Some fossil sites show a distinct pattern. Diverse dinosaur fauna in the layers below the boundary, then a gap with no fossils, then a layer with impact spherules and shocked quartz, then gradual recovery of life with no dinosaurs. The gap might be where the extinction occurred, or it might just be a period of non-deposition. We can't always tell. Statistical analyses of fossil distributions offer another approach. If you map out where different species last appear in the rock record and use statistical methods to account for preservation bias, you can estimate how abruptly the fauna changed. These analyses generally show a sharp extinction at the KPG boundary, but with some variation between groups. Dinosaurs seem to show relatively rapid extinction. Most species disappearing right at or very close to the boundary, marine reptiles likewise, ammonites. But some groups show evidence of earlier decline, certain plants, some marine plankton. The pattern isn't perfectly uniform. There's also the question of what quote 4 means. A species goes extinct when the last individual dies, but populations can be functionally extinct long before that, reduced to such small numbers that recovery is impossible. Did dinosaurs go extinct in a single bad year? Or did they decline over thousands of years, with populations shrinking, fragmenting, losing genetic diversity, until they reached a point where recovery was impossible even if conditions improved? The fossil record can't easily distinguish between these scenarios. We see the end point, the empty world after extinction. We don't see the process, the slow or fast decline of populations struggling to survive. Recent high-resolution studies of marine plankton across the KPG boundary offer some of the best evidence for extinction speed. Plankton are abundant, widespread, and they fossilize well in marine sediments. By examining plankton assemblages in closely spaced samples across the boundary, researchers can track changes in diversity and abundance. What they find is a sharp change. Plankton communities that had been stable for millions of years suddenly reorganize. Many species disappear. New species, or rare species that were previously unimportant, become dominant. The transition happens over a stratigraphic interval, too thin to measure accurately, suggesting it occurred very rapidly. Possibly in decades or centuries rather than millennia. This is strong evidence for a catastrophic cause, something that disrupted the ocean globally and suddenly. It fits the impact hypothesis well. But it doesn't rule out volcanism entirely, because a particularly intense pulse of Deccan eruptions could potentially cause rapid ocean acidification and temperature change. What we can say with some confidence is that the extinction, whatever caused it, was rapid by geological standards. Not instantaneous, but fast. Perhaps a few thousand years at most, possibly much less. The world changed quickly, and life changed with it. Sometimes what happens after an event can tell you as much about the event itself as the event's immediate effects. The recovery from the KPG extinction, the slow rebuilding of ecosystems, the emergence of new forms of life, these patterns offer clues about what kind of catastrophe preceded them. In the immediate aftermath of the extinction, the world was empty. Not literally, of course. Bacteria thrived. Fungi flourished, feeding on the dead organic matter. Small animals that could survive on detritus or stored food sources persisted, but the complex ecosystems, the multi-layered food webs, the large animals, they were gone. The first organisms to rebound were the opportunists. Ferns in terrestrial ecosystems, their spores spreading quickly across disturbed ground. Certain species of plankton in the oceans. Generalist species that could tolerate a wide range of conditions. These organisms didn't need stable ecosystems, they just needed resources and space, and both were suddenly abundant. This phase of recovery, dominated by opportunistic species, lasted for thousands to tens of thousands of years. It's visible in the fossil record as the quote 5 or quote 6 assemblages of organisms that are low in diversity but sometimes high in abundance. It's what you see after any major ecological disturbance, from volcanic eruptions to modern clear-cutting. The specialists are gone and the generalists take over. But gradually diversity returns. New species evolve, or species that had been rare before the extinction find new opportunities. In the oceans, new plankton species appear. New types of fish, eventually new marine predators, though these take much longer. On land, the forests return, but they're different forests, dominated by different plant species, and new animals move into the empty niches. The recovery timeline tells us about the severity of the extinction. After smaller extinctions, recovery is relatively quick, maybe a few 100,000 years. After the KPG extinction, full recovery took millions of years. Some niches remained empty for extraordinarily long periods. Large terrestrial predators, for example. For several million years after the extinction, the largest land predators were giant flightless birds, not the mammals or reptiles that would eventually dominate. This slow recovery suggests that whatever caused the extinction didn't just kill organisms, it fundamentally disrupted ecosystems. The soil chemistry was altered, the ocean chemistry was altered, the climate was unstable. Even after the immediate crisis passed, conditions remained difficult for complex life. If the extinction had been caused solely by a brief impact winter, you might expect faster recovery. The dust would clear, the sun would return, photosynthesis would resume, and life would rebound. But if volcanism continued after the impact, or if the impact had long-lasting effects on climate through changes in greenhouse gas levels or ocean circulation, then recovery would be slow, halting, complicated. There's evidence for continued environmental instability in the early Paleogene, the period after the extinction, temperature fluctuations, ocean chemistry changes, carbon cycle perturbations. Some of this might be from continued Deccan volcanism, some might be from the delayed effects of the impact, some might be the Earth system trying to find a new equilibrium after catastrophic disruption. One particularly interesting pattern is the recovery of reef ecosystems. Coral reefs are complex, diverse ecosystems that require stable tropical oceans. Cretaceous reefs were built by different organisms than modern reefs, mostly rudis bivalves rather than corals. These reef builders went extinct at the KPG boundary and reef ecosystems collapsed. It took 10 million years for reefs to fully recover, 10 million years of tropical oceans without substantial reef structures. That's an incredibly long time, suggesting profound disruption of ocean chemistry. Perhaps from acidification caused by the impact or volcanism, perhaps from loss of the organisms that help maintain ocean alkalinity. On land, the recovery saw the rise of mammals. During the Cretaceous, mammals had been small, mostly nocturnal, living in the shadows of dinosaurs. But with the dinosaurs gone, mammals diversified rapidly. Within 10 million years, there were mammals filling niches from tiny insectivores to large herbivores to formidable predators. This adaptive radiation was one of the most important events in Earth's history, leading eventually to primates, to apes, to humans. Would mammals have inherited the Earth if the dinosaurs hadn't gone extinct? Probably not. Dinosaurs had occupied the large animal niches for more than 100 million years. They were superbly adapted, diverse, successful. Mammals might have remained small and marginal indefinitely. The extinction created an opportunity, and mammals took it. So recovery tells us not just about the past, but about contingency, about how history might have gone differently, about the role of chance in shaping life. Science works by proposing hypotheses and testing them against evidence. The impact hypothesis and the volcanism hypothesis are the main contenders for explaining the KPG extinction, but they're not the only ideas that have been proposed. Some alternative hypotheses are more plausible than others, and examining them helps us understand why the mainstream explanations have gained such strong support. One early idea was disease. Perhaps a plague swept through dinosaur populations, driving them to extinction. It's an appealing thought because we know diseases can be devastating, but diseases are typically species-specific or at least limited to related groups. A disease that could simultaneously kill dinosaurs, marine reptiles, ammonites, many plants, and 3/4 of all species would be unlike any disease we know. It's biologically implausible, and it leaves no trace we could detect in the fossil record. Another hypothesis proposed climate change from causes other than volcanism or impact. Continental drift was rearranging land masses. Shallow seas that had covered large parts of continents were retreating. These changes could have altered climate and habitats, and indeed. The late Cretaceous was a time of significant environmental change. Sea levels were falling, climates were shifting from the extreme warmth of the mid-Cretaceous to something more moderate. These changes might have stressed ecosystems, made dinosaurs more vulnerable. But similar changes had occurred many times in Earth's history without causing mass extinctions. Why would this particular rearrangement of continents cause catastrophe? The timing is also problematic. Continental drift and sea level change occur over millions of years. The extinction was much more rapid. Some researchers have proposed that the dinosaurs were already in trouble, that diversity was declining before the KPG boundary, and that the extinction was merely the end of a longer decline. This is related to the volcanism hypothesis, since the Deccan eruptions had been occurring for hundreds of thousands of years before Chicxulub. But as we discussed earlier, the evidence for pre-extinction decline is contested, and even if dinosaurs were struggling, something still caused the final extinction, the sharp boundary visible in rock layers around the world. There was once a hypothesis about supernova explosions bathing the Earth in radiation. The idea was that a nearby star exploding could send lethal radiation toward Earth, causing mutations and extinctions. But we have no evidence for a supernova at the right time, and the extinction pattern doesn't match what we'd expect from radiation. Radiation would primarily affect surface-dwelling organisms, leaving deep-sea and burrowing animals unharmed. The KPG extinction didn't show that pattern. Another exotic idea involved a passing star disrupting the Oort cloud, the distant region of comets surrounding the solar system, sending a shower of comets toward the inner solar system. Multiple impacts over a short period could cause extinction. It's imaginative, but there's no evidence for multiple impacts at the KPG boundary. We have one crater, Chicxulub. There might be smaller impact craters from the same time period, but nothing approaching the scale needed to rival Chicxulub. Some scientists have wondered about the role of changing oxygen levels. The Cretaceous atmosphere might have been different from today's, perhaps richer in oxygen. If atmospheric composition changed, it could have affected respiration, particularly for large animals. But we have no strong evidence for a sudden oxygen change at the KPG boundary, and it's unclear what would cause such a change. What about mammals? Some hypotheses have suggested that the rise of mammals, including the evolution of egg-eating species, might have contributed to dinosaur extinction by preying on dinosaur eggs. But mammals had coexisted with dinosaurs for more than 100 million years. If they were capable of driving dinosaurs to extinction through egg predation, why would it happen suddenly at the KPG boundary? And why would mammals cause the extinction of marine reptiles and ammonites, which didn't even have eggs accessible to terrestrial predators? The reason these alternative hypotheses have not gained wide acceptance is that they either lack supporting evidence, fail to explain the full pattern of extinction, or require special conditions for which we have no proof. They serve a useful purpose, though. They remind us that science should remain open to new ideas, willing to revise explanations if better evidence emerges, and they highlight how strong the evidence for impact and volcanism actually is. We have iridium, shocked quartz, a giant crater, global wildfire markers, all pointing to impact. We have massive lava flows, climate proxies showing temperature swings, mercury anomalies, all pointing to volcanism. These aren't abstract possibilities, they're documented events, things that definitely happened. The question isn't whether an asteroid hit or whether volcanoes erupted. Both occurred. The question is which one caused the extinction, or whether both were necessary and in what proportion each contributed. When we say quote 7 in science, it's not an admission of failure. It's a statement about the state of evidence, about the limits of what we can confidently determine, about the difference between what's possible, what's probable, and what's proven. Understanding this distinction is central to understanding why we still don't know exactly how the dinosaurs died. We know many things with high confidence. We know that 66 million years ago, a large asteroid struck the Earth near present-day Chicxulub, creating a crater 150 kilometers wide. We can date this impact very precisely. We can calculate the energy released. We can model the immediate effects with reasonable accuracy. This is solid, well-supported knowledge. We also know that the Deccan traps were erupting around the same time, producing enormous volumes of lava and releasing massive amounts of gas into the atmosphere. The dating here is less precise than for the impact, with uncertainties of tens to hundreds of thousands of years, but the broad timing is clear. The most intense pulse of Deccan activity occurred close to the KPG boundary, and we know that a mass extinction occurred, eliminating 3/4 of all species, including all non-avian dinosaurs. The extinction was rapid by geological standards, probably occurring over a few thousand years at most. This is also well established. What we don't know with certainty is the causal relationship between these events. Did the asteroid cause the extinction? Did the volcanism cause it? Did both contribute? And if so, in what proportion? Did they interact in ways that made the overall catastrophe worse than either would have been alone? This uncertainty exists not because the evidence is absent, but because the system is complex. Multiple things were happening at the same time. The effects overlapped. The Earth's climate, ecosystems, and biogeochemical cycles are all interconnected. Perturbing one part affects others in ways that can be difficult to predict or retroactively determine. Consider an analogy. Imagine trying to determine the cause of death for someone who had heart disease, was in a car accident, and died in a hospital. The car accident happened. The heart disease was real. The death occurred. But what killed them? Was it trauma from the accident? A heart attack triggered by the stress of the accident? Complications during treatment? All of the above? Without detailed medical records and possibly an autopsy, you might never know for certain. The KPG extinction is similar. We have evidence of multiple stresses on the biosphere. We have evidence of a catastrophic event. We know the outcome, but determining precise causation 66 million years after the fact, with only the incomplete records preserved in rocks, is profoundly challenging. Science handles this uncertainty through debate, through ongoing research, through gradually refining our understanding as new evidence emerges. Different scientists weight different evidence differently. Some emphasize the rapidity and global nature of the extinction, seeing it as most consistent with impact. Others emphasize the pre-boundary environmental changes and the long recovery, seeing volcanism as the more important factor. Both camps can be right about their observations while disagreeing about interpretation. The fossil record does show some pre-boundary stress. The extinction was rapid. Both of these things are true, and both need to be explained by any comprehensive theory. What's important to understand is that this ongoing uncertainty doesn't mean we know nothing. We know immensely more about the end Cretaceous extinction than we did 50 years ago. We've narrowed the range of plausible explanations. We've ruled out many hypotheses. We've gathered extraordinary amounts of evidence. We're asking more sophisticated questions now than we could have even formulated decades ago. The debate between impact and volcanism is not a sign that science is broken or that we're fumbling in the dark. It's a sign that we're at the cutting edge, working on questions that are genuinely difficult to resolve, where the evidence doesn't all point in one simple direction. This is where the most interesting science happens, and there's value in acknowledging uncertainty. It keeps us honest. It prevents us from becoming too attached to particular explanations. It keeps us open to new evidence and new ideas. Science advances not through unwavering certainty, but through a willingness to revise understanding when evidence demands it. The truth about what killed the dinosaurs is written in the rocks, in the fossils, in the geochemistry. We've learned to read some of that record, but not all of it. The story is there, waiting. And as techniques improve, as we ask better questions, as we find new sites and analyze them in new ways, we come closer to understanding. Which leads us to the modern research pushing these boundaries, the new discoveries that continue to reshape our understanding. In 2016, an international team of scientists undertook one of the most ambitious geological drilling projects in decades. Their target was the Chicxulub crater, specifically the Peak Ring, a circular formation of rock that had rebounded upward after the initial impact compression. This rock had been buried for 66 million years, preserving a record of impact processes and immediate aftermath. The drilling took place offshore in the Gulf of Mexico, from a platform anchored over coordinates calculated to intersect the Peak Ring. Over 2 months, the drilling team extracted a core of rock more than 800 meters long, bringing up samples from depths where the Peak Ring material lay hidden beneath younger sediments. What they found was remarkable in its detail. The core showed the impact melt, the layer of rock that had been literally melted by the energy of collision. It showed the breccia above it, the shattered and jumbled rocks thrown around by the impact, and above that, it showed the first sediments deposited after impact, revealing what the environment was like in the months and years that followed. The post-impact sediments were thin, accumulated slowly, suggesting a world with little biological productivity. There was minimal organic material, few fossils, signs of a disrupted ocean struggling to support life. But there were also signs of resilience, microbial mats. Communities of bacteria and algae had colonized the seafloor within years of the impact. Life was returning, starting with the simplest organisms and gradually building complexity. Chemical analysis of the core allowed researchers to refine estimates of how much sulfur and carbon dioxide the impact released. The Chicxulub region in the late Cretaceous was underlain by rocks rich in gypsum and limestone. The impact vaporized these rocks, releasing enormous amounts of sulfur and carbon. The sulfur would have caused severe short-term cooling and acid rain. The carbon dioxide would have caused longer-term warming. The drilling also revealed something about the impact angle. The way rocks were deformed and distributed suggested the asteroid came in from the northeast, at an angle of about 60 degrees from horizontal. This oblique angle meant the impact was particularly effective at throwing debris into the atmosphere, maximizing the global distribution of ejecta and maximizing the environmental effects. But perhaps most interesting was what the cores revealed about life's return. In the sediments deposited in the first few decades after impact, there's evidence of algae, of simple organisms beginning to photosynthesize again. The darkness, if it existed, couldn't have been complete, or couldn't have lasted more than a few years at most. Some light was getting through, enough for photosynthesis. This finding has implications for extinction models. If photosynthesis resumed within a few years, then the extinction can't be attributed solely to prolonged darkness. Other factors must have been important. The initial heat pulse from falling ejecta, the collapse of food webs, the acid rain, the climate instability. The catastrophe was multifaceted, not reducible to a single killing mechanism. Other drilling projects have targeted KPG boundary sites around the world, building a global picture of the extinction event. Each site adds detail, reveals local effects, shows how the global catastrophe manifested in different environments. Shallow marine settings show evidence of massive tsunamis. Terrestrial settings show evidence of wildfires and plant extinction. Deep ocean sites show the collapse of plankton communities. Together, these cores are building an increasingly detailed picture of the extinction sequence. We can now talk about what happened in the first hours, the first days, the first years. We can track the progression of environmental collapse and the slow beginning of recovery. We can identify which killing mechanisms were most important in different environments, but drilling also reveals variability, complexity. Not every site shows the same effects. Some locations seem to have been devastated more than others. Recovery rates varied by region. The global catastrophe had local textures, local stories within the larger narrative. And this brings us to a crucial realization. The KPG extinction wasn't a uniform global event. It was a complex, regionally variable catastrophe that played out differently in different places. Understanding that variability is key to understanding the overall extinction. What's emerging from modern research is a picture far more nuanced than the simple narratives of earlier decades. The asteroid hit, yes. The climate changed, yes. But the details matter. The sequence of effects matters. The regional differences matter, and the interaction between multiple stresses matters. Which leads us to examine one of the most contentious questions in the entire field. Did the asteroid trigger additional Deccan eruptions, linking the two catastrophes directly? The idea is almost elegant in its simplicity. An asteroid strikes one side of the planet with enormous force. The seismic waves from that impact travel through the Earth, converging on the opposite side. When they converge, they focus energy, potentially triggering earthquakes or volcanic eruptions. It's called the antipodal effect, and it's been proposed as a way to link the Chicxulub impact directly to increased Deccan volcanism. The physics is sound in principle. We know that seismic waves from earthquakes can sometimes trigger other earthquakes or even volcanic activity. The question is whether waves from an impact, even an impact as large as Chicxulub, would be powerful enough to trigger volcanism on the other side of the planet. The Deccan traps aren't exactly opposite Chicxulub. They're offset by about 30 degrees. So the antipodal focusing wouldn't be perfect, but some researchers argue that even imperfect focusing could deliver enough energy to fracture rock, open conduits, allow magma to rise more easily. If the volcanic system was already primed, already close to erupting, then perhaps the impact provided the trigger. Dating the Deccan flows has been crucial for testing this hypothesis. If the impact triggered eruptions, there should be an increase in volcanic activity right after the Chicxulub event. Early dating studies didn't have the precision to see this clearly. The uncertainties were too large. But newer techniques, using improved methods of radiometric dating, have refined the timeline. What recent studies show is complex. The Deccan was already erupting well before Chicxulub. There were pulses of activity hundreds of thousands of years before the impact. But there does seem to be an intensification around the time of impact. The largest lava flows, the most massive eruptions, appear to cluster close to the KPG boundary. Is this evidence of impact triggering? Some scientists think so. The timing seems too coincidental to be random. Others are more skeptical. Volcanic systems have their own internal dynamics. The Deccan might have been building toward a major eruptive pulse regardless of any external trigger. The timing could be genuine coincidence, two independent catastrophes happening to overlap. There's also a question of mechanism. Even if the impact waves reach the Deccan, would they be powerful enough to trigger eruptions? Computer models of seismic wave propagation suggest that the ground shaking from Chicxulub, even at the antipode, would have been significant, equivalent to perhaps a magnitude 9 earthquake. That's severe. It could trigger landslides, cause structural damage, potentially open fractures. But would it trigger volcanism? Historical examples are ambiguous. The 2004 Sumatra earthquake, magnitude 9.1, didn't trigger any major volcanic eruptions. The 2011 Japan earthquake, magnitude 9.1, also failed to trigger significant volcanism. Large earthquakes, even magnitude 9, don't reliably cause volcanic eruptions. An asteroid impact is different from an earthquake, though. The seismic waves from impact have a different character, a more abrupt onset, potentially different frequencies, and Chicxulub was larger than any modern earthquake. The seismic energy was enormous, equivalent to multiple magnitude 9 earthquakes occurring simultaneously. Maybe that makes a difference. Recent research has looked at the Deccan lava flows themselves for evidence of impact triggering. If the impact caused earthquakes that open new fissures, those fissures might have distinctive characteristics. Some studies claim to see evidence of this, abrupt changes in the volcanic plumbing, new vents opening. Others don't see anything unusual, just the normal evolution of a large igneous province. There's also the question of whether it matters. Even if the impact did trigger some Deccan eruptions, the volcanism had been ongoing for hundreds of thousands of years before that. The environmental stress from volcanism would already have been significant. The impact triggering more eruptions would add to the catastrophe, but wouldn't change the fundamental story. Both factors contributed. But it does matter for understanding the extinction mechanism. If the impact triggered volcanism, then the two catastrophes weren't independent. They were linked, part of a cascade. The asteroid hit, triggered earthquakes, fractured the crust in distant locations, released more volcanic gases, amplified the climate disruption. It would make the overall catastrophe worse than either event alone, a synergistic disaster. The debate over impact triggering illustrates a larger point about the KPG extinction. We're trying to understand a complex system experiencing multiple simultaneous perturbations. Isolating the contribution of each factor is extraordinarily difficult. The factors interact, influence each other, create feedbacks that amplify or dampen effects in ways that are hard to predict. And this complexity extends to the extinctions themselves, to understanding why some species died and others survived. Which is what we need to explore next. Mass extinctions are not random. They don't take species by lottery. There are patterns, predictable factors that make some organisms more vulnerable than others. Understanding these patterns at the KPG boundary can tell us something about the nature of the catastrophe that caused the extinction. Body size is one clear pattern. Large animals were more vulnerable than small ones. All dinosaurs larger than a few kilograms went extinct. All pterosaurs, which could be quite large, disappeared. Large marine reptiles vanished, but small mammals survived. Small birds survived. Size clearly mattered. Why? Partly because large animals need more food. When ecosystems collapse, when primary productivity crashes, large animals starve first. They can't meet their caloric requirements. Small animals need less food, can survive on limited resources, can wait out the crisis. There's also reproduction. Large animals typically have fewer offspring and longer generation times. If populations crash, recovery is slower, and the species is more vulnerable to extinction. But size alone doesn't explain everything. Some large animals survived. Crocodiles, which can be quite large, made it through. Large sea turtles survived. So size was a factor, but not the only factor. Something about ecology mattered too. Dietary specialization seems important. Herbivorous dinosaurs that fed on specific plant types would have been doomed if those plants went extinct. Carnivores that specialized in hunting large prey would have starved when their prey disappeared. But generalists, animals that could eat many different things, had more options. Scavengers, animals that could feed on dead organic matter, might have thrived in the immediate aftermath. Habitat also played a role. Organisms living in stable, specialized habitats were more vulnerable than those in variable habitats. Deep ocean specialists, accustomed to constant temperature and chemistry, might have suffered greatly when ocean conditions changed. But organisms from coastal environments, estuaries, rivers, places where conditions naturally fluctuate, they had physiological flexibility that helped them survive. There's also the question of range. Species with small geographic ranges limited to specific regions were more vulnerable than widespread species. If the catastrophe affected different regions differently, widespread species might survive in refugia, pockets where conditions were less severe. Narrow-ranging species had nowhere to go. Reproductive strategy mattered in subtle ways. Species that invested heavily in parental care, that had few offspring requiring extended care, were at a disadvantage compared to species that produced many offspring with minimal investment. When survival becomes uncertain, quantity can matter more than quality. Produce enough offspring, and some might survive by chance alone. The pattern in marine ecosystems is particularly revealing. Plankton that lived near the ocean surface, dependent on photosynthesis, were devastated. Many species went extinct, but deep-sea organisms, those living in the dark depths feeding on organic material sinking from above, they survived better. When surface productivity crashed, the deep sea was still there, still habitable for organisms adapted to darkness and scarcity. Among plants, there's an interesting pattern related to seeds. Flowering plants that produce seeds capable of dormancy, that could wait out bad conditions, survived better than plants without this capacity. Ferns, which produce spores and can colonize disturbed ground quickly, also did well in the immediate aftermath. But plant groups without these survival strategies suffered. Looking at all these patterns together, what emerges is a portrait of the catastrophe. It was sudden enough that size mattered, that there wasn't time for large animals to adapt. It disrupted ecosystems thoroughly enough that specialists suffered, but generalists survived. It affected surface environments more than subsurface ones, suggesting atmospheric or oceanic surface effects. It reduced food availability dramatically, making dietary flexibility crucial. This pattern fits the impact hypothesis well. A sudden catastrophe affecting the atmosphere and ocean surface, causing rapid temperature change and blocking sunlight, would create exactly this kind of selective extinction. But it doesn't rule out volcanism. Intense volcanic activity could also cause climate swings, acid rain, ocean acidification, all of which would create similar selective pressures. What's becoming clear is that the extinction wasn't caused by a single killing mechanism, but by multiple stresses acting simultaneously or in rapid succession. Heat pulse, darkness, acid rain, climate swings, ocean acidification, food web collapse. Different organisms were vulnerable to different stresses. The overall pattern of extinction emerged from the overlay of all these factors, and this realization that the extinction was complex and multi-causal is shaping the way scientists think about the question. It's not, was it asteroid or volcano, but rather, how did asteroid effects, volcanic effects, and perhaps other factors combine to create the specific pattern of extinction we observe? We've never witnessed an asteroid impact like Chicxulub. We've never seen volcanism on the scale of the Deccan traps. But we have observed smaller versions of these catastrophes, events that, while not comparable in magnitude, can teach us about the kinds of effects that might have occurred at the KPG boundary. The 1815 eruption of Mount Tambora in Indonesia is one of the most violent volcanic eruptions in recorded history. It ejected so much sulfur dioxide into the atmosphere that the following year, 1816, became known as the year without a summer. Global temperatures dropped, crops failed, there were food shortages and famines. The disruption was severe, and all from a single eruption lasting a few days. Now imagine that happening not once but repeatedly over thousands of years. That's closer to what the Deccan eruptions might have been like. And while Tambora's eruption was massive by human standards, it was trivial compared to individual Deccan eruptive pulses. The scale is almost incomparable. Smaller volcanic eruptions in recent history have also demonstrated the potential for climate effects. The 1991 eruption of Mount Pinatubo in the Philippines injected about 20 million tons of sulfur dioxide into the stratosphere. Global temperatures dropped by about 0.5 degrees Celsius for 1 to 2 years. It's a measurable, documented effect, demonstrating that volcanoes can indeed cool the planet. But modern eruptions are measured in megatons of material. The Deccan eruptions are measured in millions of cubic kilometers. The difference is staggering. Extrapolating from modern eruptions to Deccan-scale volcanism requires assumptions, models, and a healthy dose of uncertainty. For impacts, we have even less to work with. The largest impact in recorded history. The Tunguska event of 1908 in Siberia was probably caused by a small asteroid or comet fragment, about 50 to 60 meters across, exploding in the atmosphere. It flattened 2,000 square kilometers of forest, but left no crater. It was a tiny event compared to Chicxulub, and it still produced shockwaves that circled the Earth. The Chelyabinsk meteor of 2013 was even smaller, about 20 meters across. And it produced a shockwave that damaged thousands of buildings and injured over 1,000 people. These events give us a sense of the energy involved in impacts, but scaling up from 20 meters to 10 kilometers is not straightforward. The effects don't increase linearly. They scale with mass and velocity in complex ways. Nuclear weapons tests, particularly the atmospheric tests of the Cold War era, provide another analogue. Large thermonuclear explosions can inject soot and dust into the upper atmosphere, potentially causing cooling. Studies of nuclear winter scenarios, developed in the 1980s, drew on these tests to understand what might happen in a nuclear war. And those studies have informed impact models, since an asteroid strike is, in some ways, similar to many nuclear explosions happening simultaneously. But nuclear weapons are still orders of magnitude smaller than Chicxulub. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, yielded about 50 megatons. Chicxulub released energy equivalent to 100 million megatons. Again, the scale is almost beyond comprehension. Modern ecosystem collapses offer insights into how extinctions might proceed. Overfishing has collapsed marine ecosystems. Deforestation has caused species extinctions. Climate change is stressing ecosystems globally. These modern examples show us how food webs unravel, how keystone species losses cascade through ecosystems, how stressed populations become vulnerable to additional shocks. The pattern is often the same. A major stress causes initial damage, then secondary effects cascade through the system, amplifying the original disruption. This is what might have happened at the KPG boundary. The impact or volcanism causes initial damage, then food webs collapse, then nutrient cycles are disrupted, then climate instability prevents recovery, and the whole system spirals toward mass extinction. Recent research has also looked at ocean acidification as a modern analogue for KPG extinction mechanisms. We're currently acidifying the oceans by pumping carbon dioxide into the atmosphere. The rate of acidification, while fast by historical standards, is still slow compared to what might have happened from Chicxulub or Deccan. Modern acidification is stressing marine ecosystems, particularly organisms with calcium carbonate shells. At the KPG boundary, acidification might have been much more severe, much faster, contributing to the collapse of marine ecosystems. What all these modern analogues teach us is that relatively small perturbations can have significant effects. And if small perturbations matter, then the enormous perturbations at the KPG boundary must have been devastating. The question is not whether they were devastating, but precisely how that devastation unfolded. Behind every theory, every analysis, every core sample and computer model, there are people, scientists who have dedicated their careers to understanding one thin layer of rock, one boundary in time. Their stories are part of the story of how we've come to know what we know about the extinction. Lewis and Walter Alvarez, the father-son team who proposed the impact hypothesis, were not paleontologists. Lewis was a physicist who had won the Nobel Prize for his work on subatomic particles. Walter was a geologist interested in extinction mechanisms. They approached the KPG boundary with fresh eyes, without preconceptions about how extinction should work. That outsider perspective allowed them to propose something radical, an asteroid impact. The reaction from the paleontological community was initially skeptical, sometimes hostile. Paleontologists had spent careers studying the fossil record, understanding its nuances and complexities. The impact hypothesis seemed to ignore that complexity, to impose a simple, external explanation on something that might have more subtle, biological causes. There were heated debates at scientific conferences, papers criticizing the hypothesis, alternative explanations proposed. But the Alvarezes kept pushing. They looked for more iridium anomalies, found them around the world. They predicted there should be a crater, and when Chicxulub was confirmed, it vindicated their hypothesis. The lesson is partly about the value of interdisciplinary approaches, of bringing different perspectives to a problem. On the volcanism side, researchers like Vincent Cortillo and Gerta Keller have been persistent voices for the importance of the Deccan eruptions. Keller, in particular, has spent decades examining KPG boundary sites, arguing that the fossil record shows a more gradual extinction pattern inconsistent with a single impact event. She's proposed that Chicxulub might actually predate the main extinction by hundreds of thousands of years, based on her interpretation of sediment layers. This claim is controversial. Most researchers disagree with Keller's dating of the Chicxulub impact, but her work has pushed the field to be more careful, to look more closely at the stratigraphic details, to not assume that all KPG boundary layers are exactly the same age everywhere. The scientific debate over the extinction has sometimes become personal, with researchers on different sides rarely finding common ground. But this tension, while occasionally unproductive, also drives the science forward. It forces both sides to gather better evidence, to refine their arguments, to address weaknesses in their hypotheses. Younger researchers entering the field now inherit this complex history. Many take a more integrative approach, acknowledging that both impact and volcanism likely played roles, focusing on understanding the relative contributions and interactions, rather than arguing for one cause to the exclusion of the other. There's also the reality that research on the KPG extinction requires resources. Drilling into the Chicxulub crater cost millions of dollars, required international collaboration, years of planning. Analysing samples requires expensive equipment, specialised expertise. Dating rocks with high precision is technically demanding. Not everyone has access to these resources, which means the science is shaped partly by who can afford to do it and where funding agencies decide to invest. Public interest in dinosaurs has also shaped the research. Dinosaurs capture imaginations in a way that, say, Cretaceous foraminifera do not. This public interest translates into funding, into media coverage, into jobs for paleontologists. The asteroid impact story, dramatic and visually compelling, has been easier to communicate to the public than the more complex volcanism hypothesis. This might have biased research funding toward impact-related questions, though in recent years, volcanism research has gained more support. There's something profoundly human about this quest to understand the extinction. We're driven partly by pure curiosity, the desire to know what happened, to solve the mystery. But there's also something deeper. Understanding how a catastrophe caused mass extinction in the past might help us understand the threats we face today. Climate change, habitat destruction, the extinction crisis we're currently living through. The KPG boundary is a case study in how planetary systems can be disrupted, how catastrophe unfolds, how life recovers or fails to recover. The scientists working on this aren't detached observers. They care about the questions, argue passionately about interpretations, spend years pursuing particular lines of evidence. The scientific method provides a framework for resolving disagreements, but within that framework there's room for creativity, intuition, persistence, and yes, the very human desire to be right. And as we move toward understanding what all this research means, what it tells us about that question we started with, why we still don't know exactly how the dinosaurs died, we need to consider what kind of answer is even possible. There's a philosophical question embedded in the scientific quest to understand the KPG extinction. It's about the nature of historical knowledge, about what it means to know something about the past that cannot be directly observed, that left only traces in rocks and fossils. We can observe the present. We can measure the iridium in boundary clay, drill cores from the Chicxulub crater, analyse fossilized shells. These observations are concrete, repeatable. Different researchers using the same techniques on the same samples should get the same results. This is the foundation of scientific knowledge. But the past itself, the actual events of 66 million years ago, we cannot observe them. We can only infer them from present evidence. An inference requires assumptions, models, interpretations. It requires connecting the evidence we have to processes we understand, to physical laws we believe apply universally. When we say an asteroid struck the Earth, we're making an inference based on evidence, iridium anomaly, shocked quartz, the Chicxulub crater. That inference is strong, well supported, about as certain as historical knowledge can be, but it's still an inference, still a step removed from direct observation. The same is true for the Deccan eruptions, for the climate effects, for the extinction mechanisms. We're building a picture of the past from incomplete fragments, using our understanding of how the world works to fill in the gaps, and sometimes those gaps are large. This doesn't mean all inferences are equally valid. Some are much better supported than others. The evidence for Chicxulub impact is overwhelming. The evidence that the impact had global environmental effects is very strong. The evidence that these effects caused or contributed to the extinction is substantial but more circumstantial. With volcanism, we know the eruptions occurred. We can model their climate effects with reasonable confidence. But linking those effects definitively to specific extinction patterns is harder. The timing is less precise, the effects are more gradual, more diffuse, harder to pin down in the geological record. So when we ask what killed the dinosaurs, we're really asking something more subtle. We're asking which of the catastrophic events we know occurred was most responsible for the extinction pattern we observe. And the answer depends on how we weight different types of evidence, how we interpret ambiguous data, what assumptions we make about processes we can't directly observe. Different scientists, equally competent and honest, can look at the same evidence and reach different conclusions because they weight the evidence differently. One might emphasize the rapidity of the extinction, seeing it as evidence for impact. Another might emphasize the ecological stress before the boundary, seeing it as evidence for volcanism. Both are being reasonable, working within the bounds of scientific methodology. This is why the uncertainty persists, not because we lack evidence, we have vast amounts of evidence, but because the evidence doesn't all point unambiguously in the same direction. The story is complex, multi-layered. The catastrophe was not a simple single event, but a cascade of interactions. Perhaps the question itself needs reframing. Instead of asking, was it asteroid or volcano, perhaps we should ask, how did multiple factors combine to create conditions where extinction became inevitable? That's a more complex question, harder to answer with a simple soundbite, but it's probably closer to the truth. There's also the question of what level of certainty is achievable for historical events. In physics, we can perform experiments, test hypotheses repeatedly, achieve high levels of certainty. But historical sciences like paleontology and geology deal with unique events that can't be repeated. We can't rerun the KPG extinction to see if a different outcome is possible. This means historical knowledge has inherent limitations. We can achieve high confidence, strong support, consensus among experts. But we may never achieve the kind of certainty that comes from direct observation or repeatable experimentation. We're always working with incomplete information, making our best inferences, acknowledging that new evidence could revise our understanding. And that's not a weakness. It's the nature of the endeavour. The past is real. It happened. But our knowledge of it is constructed, provisional, always open to refinement. The goal is not perfect certainty, but the best explanation we can build from available evidence. And part of what makes this particular mystery so enduring is that it matters. Not just to scientists, but to anyone who thinks about life's fragility, about how quickly a world can change, about what it means that we're here now, the descendants of the small mammals that survived when the giants fell. The KPG extinction is not just ancient history. It's a case study in how planetary systems respond to catastrophic perturbations, how ecosystems collapse and recover, how life persists or fails to persist in the face of radical environmental change. And those lessons feel increasingly relevant as we face our own environmental crisis. We're changing the planet's climate, pumping carbon dioxide into the atmosphere at rates that, while not as sudden as Chicxulub, are extremely fast by geological standards. We're acidifying the oceans, disrupting nutrient cycles, causing species extinctions. We're not facing an asteroid impact or supervolcano, but we are stressing the Earth system in ways that might have unpredictable consequences. The KPG extinction teaches us that complex systems can collapse surprisingly fast. Ecosystems that had been stable for millions of years unraveled in thousands of years, perhaps less. The dinosaurs had survived other environmental challenges, other climate changes. They were successful, diverse, well adapted. But when the crisis came, adaptation happened too slowly. Populations crashed before evolution could save them. This is a warning. Modern species are experiencing rapid environmental change. They're losing habitat, facing new diseases, dealing with altered climates. We assume they'll adapt, migrate, find ways to survive. But the KPG extinction suggests there are limits to adaptation speed. Push too hard, too fast, and you cross a threshold where recovery becomes impossible. The extinction also teaches us about interconnection. When primary productivity crashed, herbivores starved, and then carnivores followed. The loss of one component triggered cascading failures throughout the ecosystem. Modern ecosystems are similarly interconnected. The loss of pollinators affects plants. The loss of predators affects prey populations. Changes in one part of the system propagate. We sometimes think of extinction as affecting other species, not us. but humans depend on ecosystem services: clean water, breathable air, pollination, nutrient cycling, climate regulation. If those systems collapse, we collapse with them. We're not separate from nature, immune to its perturbations. We're embedded in it. The KPG extinction also demonstrates the importance of refugia, of places where conditions remain tolerable even during global catastrophe. Species that survived often did so by persisting in small populations in favourable locations, then re-expanding when conditions improved. For modern conservation, this suggests the value of protecting diverse habitats, creating corridors between them, maintaining genetic diversity that allows populations to adapt. There's also a lesson about timescales. The KPG catastrophe was rapid by geological standards, but still took thousands of years. Modern climate change is happening over decades to centuries. That's incredibly fast geologically, but it's also slow enough that we have time to respond, to change course, to mitigate the damage. We're not facing an asteroid impact that gives us hours to react. We have years, decades even, to make different choices. But the extinction also shows that recovery takes far longer than collapse. The world before the KPG boundary was destroyed in perhaps a few thousand years. Recovery took millions of years. Ecosystems rebuilt, but they were different. The dinosaurs never returned. New groups, mammals and birds took their place. This is perhaps the most sobering lesson. Some changes are irreversible on human timescales. Once you lose something, it may be gone for millennia or forever. The debate over what killed the dinosaurs, whether it was impact or volcanism or both, also carries a lesson about how we understand and respond to complex crises. It's tempting to look for single causes, simple explanations. The asteroid killed the dinosaurs. Climate change will cause extinctions. But real systems are usually more complex. Multiple factors interact. Acute crises meet chronic stresses. The whole becomes more than the sum of its parts. This means we need to think systemically about modern environmental challenges. Climate change isn't the only threat. Habitat loss, pollution, invasive species, disease, all interact. Addressing one problem while ignoring others may not be sufficient. We need comprehensive approaches, acknowledging complexity, preparing for cascading effects. And perhaps most importantly, the KPG extinction reminds us of life's resilience. 3/4 of all species went extinct. It was a catastrophe almost beyond imagination, but life survived. It persisted, adapted, diversified. Within 10 million years, ecosystems had recovered. Within 66 million years, those small mammals that hid from the catastrophe had given rise to humans, to consciousness, to science that could look back and try to understand what happened. Life is fragile but also astonishingly persistent. The question for our time is whether we'll be part of the collapse or part of the recovery. There's something almost poetic about the fact that we still don't know exactly what killed the dinosaurs. After decades of research, countless studies, millions of dollars spent on drilling and dating and analysis, the question remains partially open. And perhaps that's as it should be. Science sometimes gives us clear, definitive answers. The Earth orbits the Sun. DNA carries genetic information. Water is composed of hydrogen and oxygen. These are settled questions, supported by overwhelming evidence, unlikely to be overturned. But many of the most interesting questions in science don't have simple answers. They have nuanced, qualified, provisional answers that evolve as we learn more. The KPG extinction is one of these. We know many things with high confidence. We know when it happened, what went extinct, what survived. We know an asteroid struck. We know volcanoes erupted. We know the climate changed and ecosystems collapsed. But the precise causal chain, the relative importance of different factors, the exact mechanisms by which different species went extinct, these remain subjects of active research and ongoing debate. And that's beautiful in its way. It means there's still mystery in the world, still questions to pursue, still discoveries to make. Every new core drilled, every new fossil found, every new analytical technique developed has the potential to shift our understanding. The story isn't finished. We're still writing it. This openness also keeps us humble. Science is powerful, has given us extraordinary understanding of the natural world, but it doesn't have all the answers, at least not yet. There are limits to what we can know, especially about unique historical events millions of years in the past. Acknowledging those limits is a kind of intellectual honesty. It also prevents the story from becoming stale. If the KPG extinction were fully understood, settled, closed, it would lose some of its fascination. It would become a fact to memorize rather than a mystery to explore. The ongoing uncertainty keeps it alive, keeps people engaged, keeps researchers motivated to dig deeper. There's also value in the debate itself, in the process of scientists proposing hypotheses, testing them, arguing about interpretations. This is how science self-corrects, how bad ideas get filtered out and good ideas refined. The fact that there's still disagreement about the extinction doesn't mean science is failing. It means it's working, that researchers are critically examining claims, demanding high standards of evidence, not settling for easy answers. And the uncertainty reflects something real about the world. It's complex. Simplicity is appealing, but nature doesn't always cooperate. The dinosaurs probably didn't die from a single cause in a single moment. They died from a cascade of interacting catastrophes, each amplifying the others, creating conditions where even the most successful animals couldn't survive. Understanding that complexity is harder than understanding a simple story, but it's more accurate, more true to what actually happened. There's also a kind of comfort in not knowing everything. It leaves room for wonder, for imagination, for the possibility of surprise. What if we discover that the impact triggered a cascade we haven't considered? What if we find evidence of a third factor we haven't even thought to look for? The unknown is not an emptiness, but a space of possibility. In some ways, the mystery of the KPG extinction is a gift. It invites us to think deeply about causation, about evidence, about how we know what we claim to know. It's a masterclass in scientific reasoning, in dealing with uncertainty, in building knowledge from incomplete information. Students learning about the extinction are learning not just paleontology, but epistemology, the theory of knowledge itself. And for those of us who simply wonder about the world, who look at fossils in museums and imagine ancient landscapes, the uncertainty makes the dinosaurs more present somehow. They're not a closed chapter, but an ongoing story. Every time we look at their bones, we're looking at a mystery, at questions that brilliant people have devoted their lives to answering and still haven't fully solved. The dinosaurs are gone. That's certain. But exactly why they're gone, exactly how the catastrophe unfolded, exactly which blow was fatal, these questions linger, suspended between what we know and what we're still discovering. And in that space between knowledge and mystery, there's room for something essential to the human experience. The acknowledgement that we don't have all the answers, and that seeking answers is, in itself, meaningful. Which brings us gently to think about what this all means. What we take away from this long journey through evidence and theories and debates. 66 million years is a number that's difficult to truly comprehend. It's far beyond human experience, beyond recorded history, beyond the span of our species' existence. Anatomically, modern humans have been around for perhaps 300,000 years. All of recorded human history covers maybe 5,000 years. 66 million years is more than 10,000 times longer than all of human civilization, and yet, in geological terms, 66 million years is relatively recent. The Earth is 4.5 billion years old. 66 million years is less than 2% of the planet's history. It's the blink of an eye in deep time. The dinosaurs lived in what is, geologically speaking, the recent past. Their extinction is a recent event. This double perspective that 66 million years is both impossibly long and relatively short is one of the mind-bending aspects of thinking about deep time. It forces us to expand our sense of scale, to imagine time spans our brains weren't evolved to grasp. In those 66 million years since the extinction, continents have drifted. India has collided with Asia, pushing up the Himalayas. The Atlantic Ocean has widened. The climate has oscillated between hothouse conditions and ice ages. Life has diversified, with mammals and birds radiating into countless new forms. Humans evolved from small primate ancestors, developed consciousness, language, culture, technology. We've walked on the moon, sent probes beyond the solar system, decoded the genome. All of that happened in the time since the dinosaurs died. And yet the rocks from that time, the boundary layer with its iridium and shocked quartz, they're still here, preserved, waiting to be studied. The past is not truly gone. It's encoded in the present, if we know how to read it. This persistence of evidence across vast time spans is part of what makes geology and paleontology possible. The past leaves traces, not complete records, but fragments, clues, pieces of a puzzle that we can gradually assemble into something approaching understanding. Every fossil, every rock layer, every chemical signature is a message from deep time. And what is the message from the KPG boundary? Perhaps it's this: world's end. Not the planet itself, which persists, adapts, continues, but the ecosystems, the communities of life, the particular arrangements of species that dominate at any given time. These can be destroyed. Stability is not permanence. Success is not security. The dinosaurs ruled for 165 million years, far longer than mammals have dominated, far longer than humans have existed, and still. They fell. This is both sobering and somehow reassuring. Sobering because it reminds us that nothing lasts forever, that we are part of systems that can collapse, that even the most successful forms of life are vulnerable. But reassuring because it also tells us that endings are not final. After the extinction came recovery. New forms of life emerged. The world rebuilt itself, different but still vibrant, still creative, still generating complexity and beauty. We are the inheritors of that recovery. We exist because small mammals survived when dinosaurs didn't. Our lineage, our evolutionary history, our very existence is shaped by that catastrophe 66 million years ago. If the asteroid hadn't hit, or if it had been slightly smaller or struck at a different angle or hit a different part of the planet, history might have been different. The dinosaurs might have survived. Mammals might have remained small and marginal. Primates might never have evolved. Humans might never have existed. This is the contingency of history. Things could have gone differently. Our presence here is not inevitable, not predestined. It's the product of countless chance events. Branch points where one outcome occurred rather than another. The KPG extinction was one of those branch points, one of the most significant in Earth's history. And yet here we are, 66 million years later, trying to understand what happened, using science and technology that wouldn't exist if the extinction hadn't occurred the way it did. There's something almost circular about it, something deeply strange. We're products of the event we're studying, trying to understand the catastrophe that made our existence possible. In thinking about the extinction, we're really thinking about ourselves, about where we came from, about the long chain of events and accidents that led from Chicxulub impact to human consciousness. We're thinking about time and change and the impermanence of all things. And we're thinking about how to live in a world where catastrophe is possible, where stability is temporary, where the future is always uncertain. So we come to the question we started with, carried now through hours of evidence and theory, through impact craters and volcanic flows, through fossils and chemical signatures, through debates and uncertainties. Why don't we know, exactly and definitively, what killed the dinosaurs? The answer, if we can call it that, is that the question asks for a kind of certainty that may not be achievable. Not because the evidence doesn't exist, but because the event was complex, multi-causal, a convergence of catastrophes that interacted in ways we're still trying to understand. We know an asteroid struck. That's as certain as any historical knowledge can be. The crater is there, the iridium is there, the shocked quartz is there. The impact happened, and it was enormous, catastrophic, globally disruptive. We know the Deccan was erupting, releasing vast quantities of gas, changing the climate, acidifying the oceans. The lava flows are there, the chemical signatures are there, the timing aligns with the extinction. The volcanism happened, and it was sustained, intense, environmentally devastating. We know that 3/4 of all species went extinct around the same time, rapidly by geological standards, in a pattern that suggests catastrophic environmental disruption. The extinctions happened, they were severe, they transformed life on Earth. What we don't know with absolute certainty is how to apportion responsibility among these factors. Was the asteroid sufficient to cause the extinction on its own? Would the Deccan eruptions have caused mass extinction even without the impact? Did the two catastrophes interact, each making the other worse? Did the impact trigger more volcanic eruptions? Did the volcanism weaken the biosphere, making it more vulnerable to impact? These are the questions that remain open, that different scientists answer differently based on how they interpret the evidence. And perhaps the most honest answer is that all of these factors mattered, that the extinction was overdetermined, that multiple causes converged to create a catastrophe that no single factor alone would have produced. The impact provided acute shock, heat, darkness, immediate disruption. The volcanism provided chronic stress, climate instability, ocean acidification, prolonged disruption. Together, they created conditions where recovery became nearly impossible, where even small animals struggled to survive, where ecosystems collapsed from both sudden trauma and sustained pressure. This is a more complex answer than an asteroid killed the dinosaurs, or volcanoes killed the dinosaurs. It's less satisfying in some ways, harder to reduce to a simple statement, but it's probably closer to the truth, closer to what actually happened on that planet 66 million years ago. And in acknowledging this complexity, in accepting that we don't have a single simple answer, we're not admitting defeat. We're being honest about the nature of historical knowledge, about the limits of evidence, about the complexity of natural systems. We're recognizing that the world is richer, more intricate, more subtle than our simplified narratives often suggest. The mystery of the KPG extinction will likely persist. New evidence will refine our understanding, shift the balance of probability, answer some questions while raising new ones. But there may never be a moment when we can say, with complete certainty, exactly what happened, exactly which factor was most important, exactly how the catastrophe unfolded hour by hour and year by year. And perhaps that's appropriate. The extinction was a hinge point in Earth's history, a moment of profound transformation that shaped everything that came after. It deserves to be treated with complexity, with nuance, with an acknowledgement that simple answers may not capture its full reality. We stand here, 66 million years later, the descendants of survivors, looking back at a world destroyed and reborn. We've learned to read rocks, to decode chemical signatures, to model climate and ecosystems. We've built technologies that let us drill into impact craters and date minerals with extraordinary precision. We've accumulated vast amounts of knowledge, and still the question remains partially open, hanging between what we know and what we don't, between certainty and mystery. That space, that gap between knowledge and ignorance, is where science lives. It's where curiosity drives us forward. It's where we acknowledge that understanding the world is an ongoing process, never complete, always reaching for truth while recognizing it may remain partially beyond our grasp. The dinosaurs died. How exactly? We're still working on it. We're closer than we've ever been, and we'll keep getting closer. But the final answer, the complete picture, may always be slightly out of reach, preserved in rocks but not quite fully legible, a story written in stone that we're still learning to read. We've travelled together for 2.5 hours now, drifting slowly through 66 million years of geological time, through impact craters and volcanic provinces, through fossils and chemical signatures, through debates and discoveries. Thank you for staying this entire journey, for lending your attention to this ancient mystery, for thinking with me about what we know and what we're still trying to understand. From the thin layer of clay that circles the globe to the massive crater buried beneath the Yucatan, from the vast basalts of the Deccan traps to the tiny fossils that record ecosystem collapse, we've explored the evidence for what killed the dinosaurs. We've seen that the answer is not simple, that both asteroid and volcano left their marks, that the extinction was complex, multi-causal, a convergence of catastrophes that transformed life on Earth. The answer, as honestly as I can give it, is that we don't know exactly what killed the dinosaurs because the event was too complex for a single explanation. Both impact and volcanism played roles, perhaps interacting, perhaps amplifying each other, creating conditions where even the most successful animals in Earth's history couldn't survive. The uncertainty that remains is not a failure of science, but a reflection of reality, of a world richer and more intricate than our simplified narratives can capture. If you found something meaningful in this exploration, a like or a subscribe helps others discover these calm journeys through deep time. And if you have thoughts or questions, if something resonated or puzzled you, I'd love to hear about it in the comments. To those who've been here before, who return to these slow drifts through science and history, thank you. You make this work feel worthwhile. Wherever you are in the world right now, whether it's night or approaching dawn, whether you're already drifting towards sleep or still listening closely, I hope you feel comfortable. I hope your breathing has slowed, deepened, steadied. I hope your thoughts have quieted. Your body feels heavy and warm, held safely by whatever surface supports you. I hope the concerns of the day have faded, at least for now, leaving you in this peaceful space between waking and sleeping. Look up at the stars if you can, or imagine them above you even if you can't see them. 66 million years ago, those same stars looked down on a different world, on dinosaurs walking beneath them, unaware that their time was ending. And 66 million years from now, different eyes will look up at those same stars, perhaps wondering about us, about this moment we're living in, about what we understood and what we missed. But that's far in the future. Right now, in this moment, all that matters is rest. The mysteries will still be there tomorrow. The debates will continue. Researchers will keep drilling, dating, analysing, refining our understanding. The story will go on. But for now, for tonight, it's enough to have thought about it, to have touched this ancient catastrophe gently, to have acknowledged both what we know and what remains beautifully unknown. Sleep well. Dream, if you dream, of ancient forests and shallow seas, of asteroids falling through space, of volcanoes building mountains slowly over ages, of the small mammals that survive to become us, of time stretching backward and forward, of mysteries written in stone. Dream of a world that ended and a world that began, of extinction and recovery, of life's persistence against all odds. Thank you for being here. Thank you for listening. Thank you for caring about this old, beautiful mystery. Good night.